All right. The name of chapter 2 is Scientific Measurements. Measurements. Every time we make a measurement, there is an error associated with that measurement. And we need to be able to understand that, the fact that there's an error, to know the limitations of our own measurements. Right now, the coronavirus thing is going on, and you get so much information about people who have tried to determine whether the coronavirus is causing problems here, causing problems there. This medicine is helping, this medicine isn't helping. Some days they say the coronavirus is getting better, some days they say it's getting worse, right? And the reason for this is because it's not simple to make measurements, and there's often errors in the measurements. But that doesn't mean we don't make measurements. That just means we have to be aware of the measurements limitations. All right? So this chapter will help us recognize our limitations. And when somebody says, oh, this is the right value, we'll be able to know what they mean. Because they don't mean this is the only exact right value. They mean this is the value we got based on these types of measurements and under these conditions. And scientists understand that. A lot of times the news people don't understand that. And they think, oh, this is the truth, the only truth. But science fluctuates and changes because of the limitations of the measurements. So we need to have an understanding about that. So, to begin our conversation about measurements, we're going to talk about the different things that we measure, like the physical property of a material, like the melting point of a material. So, you know what happens when we melt something. It goes from a what to a what?
A solid. It goes from a solid to a liquid.
That's right, a solid to a liquid. And so if I have solid water going to liquid water, I'm melting it. Very good. Now, here's a little test for you. Is this a chemical reaction or is it a physical reaction?
Physical.
Yeah, it's a physical reaction. How could we tell? Just because we remember, or is there some other way? What are the ways we can tell?
Because it's staying the same thing, it's just changing its shape.
Changing its state. That's right. That's exactly right. So when the chemistry changes, then that's how you know you have a chemical reaction. That's also a reminder why you can't just put numbers down here to balance the equation, because it changes it chemically. So things like melting point, it's the temperature that you need to get solid to go to liquid. Or boiling point, the temperature you need to get the liquid to go to the gas. The vapor pressure, that's something we'll introduce in the future, but it's the pressure that results when there's a gas inside a balloon, for example. Color of a material, its state of matter, how hard it is, right? Electrical conductivity. Some materials will conduct electricity, like pans that are metal will get hot on the stove really fast, but other stuff won't. Like a ceramic pan, you can put in the microwave, a glass plate, and it'll get hot, but it won't get nearly as hot as other types of material will. For example, you put metal in the microwave and it'll get really hot really fast, so much so that it'll melt through the bottom of your microwave, and that's why you don't put metal in the microwave. So all these are physical properties. Chemical properties all have to do with reactions, some sort of a reaction occurring. So you can usually identify a phrase like these ones, like reacts with other elements, ability to act as a reducing agent, oxidizing and reducing. Those are terms that we'll introduce later. They're different kinds of reactions. So when something actually reacts, we usually have a phrase that helps us recognize. It's a change in that chemical's properties, or that it becomes a different chemical, therefore it has different properties. Okay, so let's see if we can figure out whether these phrases represent chemical changes, or chemical properties, or physical changes, or physical properties. What do you think? Magnesium metal is gray. Is that a chemical property of magnesium or a physical property of magnesium? Physical.
Chemical.
No,
Physical.
it's physical. Color is physical. Very good. How about magnesium metal tarnishes in air? Do you know what tarnishes means?
That's chemical reaction.
That's right. It kind of like rusts, just like some baking pans will get a brown around the edges. That rust, that's reacting with the oxygen. Magnesium metal melts at 922 Kelvin. Is that a chemical property or a physical property?
Physical.
Physical, that's right. The melting of magnesium is changing it from solid to liquid, so that's just a physical. Magnesium reacts violently with hydrochloric acid. Chemical property, right? You're getting something different forming. The magnesium is changing from solid magnesium to magnesium chloride. Okay, it's a lot easier when you see the chemical reaction, huh?
Yeah.
All right, here's another one. Let's see if we can watch this video. In this video here, we have a bathtub, little baby bathtub. What do you call those? Little baby pool, right? Little kid pool. And we have a stand. And on the stand, we have, right here, we have a little piece of sodium metal right there. And watch it, it drops into the pool. It dropped in, see it? And it explodes. All right? So, which of the following is a chemical property? Water is colorless. Water reacts violently with sodium metal. Water, yeah, that one. Water boils at 373. Both this one, water is colorless, and water boils at 373, are physical properties, right? Very good. You know why that sodium is blowing up like that when it hits the water?
No.
It's because, let me get my periodic table here. Where is my periodic table? There it is. It's because sodium, right here, has 11 electrons and 11 protons, right? And sodium, along with everybody else, wants to have the same number of electrons as the noble gases. Have you heard of the noble gases before?
No.
This column right here on the periodic table that contains helium, neon, argon, krypton, xenon, and radon, those are our noble gases. And all the other elements wish they could be like the noble gases. Now, they can't change their number of protons. Just can't do it in chemistry. Sodium has 11 protons, so it can't change its number of protons. However, it can change its number of electrons. Atoms can change their number of electrons. How many electrons would sodium, what would sodium have to do if it has 11 electrons and it wants to be like a noble gas in terms of its electrons? What could it do?
It has to gain some or it could lose some.
That's right. It has to gain how many?
Which one does it want to be?
It wants to be like anyone in here on this list.
It has to gain 7.
Gain 7 or what? -1. That's right. It wants to gain 7 or -1. And because it's so close, it just has one extra electron. Whenever you put sodium metal with anything, it'll just give that electron up so fast. It'll react very fast. So sodium metal always wants to give up one electron to be like neon. Now, it can't gain 1, 2, 3, 4, 5, 6, 7 electrons very easy. That takes so long. Too many electrons. Nobody wants to give up that many electrons. So it can lose that electron. It finds it easiest to lose that electron really fast. And when it interacts with water, it gives that electron to water right away. And water takes that electron and forms hydrogen gas. And then that hydrogen gas explodes. So that's the explosion that we're seeing in that video. Okay. So here's a little slide that shows what's happening when you have a physical reaction of melting. Water's a liquid going to a solid. Sorry, this isn't free melting. What is this? If it's going from a liquid to a solid, what do you call that? What do you call it when it goes from a liquid to a solid?
Physical reaction.
It's physical reaction. And what specifically is it doing if it's going from a liquid to a solid?
It's freezing.
That's right. We're freezing this water. And see what really is happening is our thermometer is measuring how fast the molecules are moving. So when we reach a lower temperature, the molecules are just moving slower. Okay, let's watch this video here about the different states of matter.
Solid, liquid, gas.
Okay, let's try that again. Okay, so let's watch this video now.
Matter can be found in any of 4 states: solid, liquid, gas, or plasma. Solid can be changed to liquid by melting. Solids can change directly to gas in a process called sublimation. Liquid is changed to gas by boiling. Gas can condense to liquid. Solids can be formed directly from gas by crystallization. A plasma is a group of positive ions and unbound electrons. Plasmas can be produced by energizing gases to give up electrons, as in this neon sign and fluorescent tube. The sun is also a plasma. Over 99% of the matter found in the universe is in the plasma state.
All right. So that introduces us to our states of matter, our different states of matter. And we've talked a little bit about this, and you probably already know a lot about it. But we have solids, liquids, and gas. And those are the states that we're generally going to be talking about in this class. Plasma is an interesting state and very important for a lot of technology. Most of our light bulbs nowadays rely on plasma. But in class, we don't talk a lot about plasma. Okay? One more example here is our example of our chemical reaction. Here we have HCl. This green dot is the chlorine, the white dot is hydrogen, dropping into the water. And when it goes into the water, the hydrogen and the chlorine separate like that. And you get this reaction. And again, we can recognize this chemical reaction when or by the change that occurs. Over here, the hydrogen is with the chlorine, and now the chlorine is by itself, and the hydrogen has gone with the water. So we can recognize that chemical reaction pretty easily. This video here talks about ionic compounds. Now let's have a quick little review about how we can tell the difference between a molecular compound and an ionic compound. Let's, yeah, go ahead. Which one?
Ionic can have metal in anything, but molecular cannot have metal at all.
Very good. Only non-metals. And this one contains a metal and non-metal. Very good. Now I'm going to show you why it's important that we separate these in terms of how we think about them. This video is going to explain why it's important to kind of think about them differently. It's going to show how ionic compounds kind of reside, what they look like. All right? I'm going to mute the video and I'm just going to talk to you about what we see. Ionic compounds reside in this form, which is called a three-dimensional lattice. So this is an example of the ionic compound NaCl, sodium chloride, where the green spheres are chloride ions and the white spheres are sodium. So in this ionic compound, you don't just have one Na and one Cl in a pair moving around. You have lots of NAs and lots of Cls gathered together in this three-dimensional lattice. Can you say three-dimensional lattice?
Three-dimensional lattice.
Very good. And all ionic compounds come like this, as three-dimensional lattices. All right? Now, molecular compounds are different. Whoops. Let's see what happens when we put this molecular or ionic compound into water. So here are our sodium ions, and we'll talk about what ions mean. There's chloride ions. We'll talk about that later on. And when we put them into water, I don't know if you've ever put salt into water, but the water molecules, now here you see how water molecules reside. See the water molecules? It's red oxygens with each one having two white hydrogens, right? Water has no metals. Therefore, it's what kind of a compound? Not ionic, but what?
Molecular.
Molecular, that's right. And that means that the unit is what the formula is. The H2O is its unit, and it travels around in that unit. So we can watch the water molecules surround the chlorine here and pull it away. The same thing happens to the sodium. The water surrounds the sodium and pulls it away from the three-dimensional lattice. As the surface atoms are pulled away, then the rest of the water can come in and begin to pull more of the ions away. And that's why when you put an ionic compound into water, it will dissolve like that. It dissolves and disappears in the water. You can't see it anymore. Sometimes you can see the color that's left behind, like this ionic compound called copper sulfate. It's blue. It's a blue, solid, ionic compound, three-dimensional lattice. So when you put it into water, it turns the water blue. All right? But you don't see any more crystals hanging around. After a while, they'll dissolve. Everything will dissolve. Okay, and we'll talk more about this term dissociate in the future. For now, though, it's an important time for us to recognize the difference between molecular and ionic compounds. Ionics contain metal and nonmetal, while molecular only contains nonmetals. Okay, one more slide and then we're done. Which one of the following represents a physical change? Let's see if you can pull it out. It's a hard one. This is a hard slide because you might not be familiar with all the things that are happening. But think about the idea of new chemicals and something new occurring and changing the properties completely. Let's see if we can figure it out. Which one kind of looks obvious to you? Any of them? B. Grape juice. Oh, C as in cat?
No,
E.
Elephant.
Elephant. When ignited with a match in open air, paper burns. Is that a physical change or a chemical change?
Physical?
Physical. What is happening to the paper? Do you know?
It's
What is it? What is it change or what's it becoming?
becoming ash.
Ash. That's right. And what is ash? So paper is made up essentially of the same thing as sugar, and we combine it with oxygen. That's what we do when we burn it. I don't know if you've ever recognized, but to keep a campfire going, you need to keep fanning it because you need to keep pushing more oxygen in there. If you just leave it alone, it'll burn up all the oxygen around that area, and then it'll stop reacting because it can't work. Early on, they did some experiments where they would take a container like this, and they would put a little mouse in the container. Nobody would do this nowadays, but this was before they understood what oxygen was. And they would take a little tiny piece of cotton, and they would light it on fire and drop it in there, and they would plug it up. And the fire would burn all the oxygen, and then the mouse couldn't breathe, and it would start moving around. So they'd have to open this up to let the air come back in. So they found out early on that when you burn, you are taking up the oxygen. So you take up the oxygen and you form carbon dioxide and water, and sometimes you leave behind black carbon ash. So this is the reaction. Does that look like a chemical reaction or a physical reaction?
Chemical.
Yeah, that's a chemical reaction. So when you burn paper, that's a chemical reaction. What else? What other ones look like you might know, even if it's a chemical reaction? Do you know any of these that are chemical reactions for sure?
Is the grape juice physical?
Grape juice, when left in an open, unrefrigerated container, turns sour. What's happening there? What's happening is the sugar, again, same formula, combines with, sometimes it combines with oxygen, depending on if the lid is open or not. But if the lid's not open, the sugar will be broken down into carbon dioxide and ethanol. And that is, ethanol. That is the main component, not main component, but that's what that's the difference between grape juice and wine, right? If you leave out fruit or sugar, anything that has sugar, out and let it react with the yeast or any bacteria that gets in there, then there's a chance that you will make alcohol from your sugar. So that is a chemical reaction also. Let's keep looking. B is a chemical reaction because the sugar is changing to alcohol, to ethanol.
No, but
Oh, E? E is a D as in dog. You think D is a what?
Yeah.
Physical or chemical?
physical.
Physical. That's right. When water condenses, it's just changing from a gas to a liquid. And I don't know if you've ever had a cold cup of water and set it on the table, and then you come back maybe a little bit later and you see that there's water on the outside of the cup and on the table. Did the water leak through the cup?
No.
No, the water didn't leak. What did it do?
Basically sweat.
It sweats, but it's not coming from the inside, is it? The air, the water in the air on the outside sticks to the side of the glass and then condenses there and forms liquid. So right now in the air, there's water. Water. And if you've ever been to a place like California or Utah or states that are dry like Nevada, then there's less water in the air, right? But in some states there's more water. And where there's more water, it's more easy to condense. So that's right. That is an example of a physical change. Okay, very good. We've learned a lot today. We learned about physical and chemical changes a little more, physical and chemical properties. And we also learned a little bit about ionic and molecular compounds, which is really cool. Okay, we'll see you next time.